So in this video, we're going to be talking about linear inequalities. So linear meaning line, and inequality meaning not equal. So when I'm talking about linear inequalities, I'm talking about equations that are lines, equations meaning equal, but instead of being equations, they're going to be inequalities. They're going to be things that don't have an equal sign in them. They're going to have greater than or less than. So before we get into those, let's talk about some linear equalities to start out, right? The good old linear equalities that we are used to. So let's do one. How about x equals 2, right? That's an equality. It's linear because x is only to the first power, no squares or square roots here or anything crazy. So x equals 2. If we were to graph that, we would draw our coordinate plane out. Let me do that in purple. We would draw our coordinate plane, and we would find where x equals 2. Well, x equals 2. Here's the x-axis and the y-axis. X equals 2 right here. So x is 2. But we also need to know about y, and this doesn't say anything about y. So it includes all possible y values. And of course, y is up and down, so we go up and down. So x equals 2 is a vertical line because that's where x is 2. Any point on this line, if you were to look at these coordinates, all have 2 for x. Right here is 2 comma 1, here's 2 comma 2, 2 comma 3, 2 comma 4. The first number is always 2. X is always 2. Y could be anything, right? 2 comma infinity is up here, maybe 2 comma 7, negative 7 is down here somewhere, but 2 is the constant, right? It's the thing that's always the same. X is 2. So that's the line x equals 2. If I were to talk about a different equality, maybe one that starts with a y equals maybe minus 3. I could graph that as well. So y is negative 3. Well, again, here's our y-axis, here's our x-axis. So which axis is y on? Well, y is going to be on this axis. So where is y negative 3 on this axis? Right here. So that's where y is negative 3. It doesn't say anything about x here, and we need to know what we do with x. So for this, we go left and right for all possible x values. Any point on this line is going to have a y value of minus 3. All of these points are something comma negative 3. So it's where y is negative 3 is on this line. So for instance, this is negative 2 comma negative 3. This one over here is 4 comma negative 3. This is 6 comma negative 3. This is 1, 2, 3, 4, 5, negative 5 comma negative 3. So every point in this line has negative 3 for its y value. So y equals negative 3 is going to be a horizontal line. It's kind of goofy because y you think vertical, but it turns out to be a horizontal line, and x you think horizontal, and it ends up being a vertical line. So if we were to take these and make them inequalities, what we're doing is getting rid of the equal sign. So I'm going to do the same thing. This time, instead of x equals 2, I'm going to say x is greater than 2. So I'm going to draw my coordinate plane, just like before. And I'm going to graph this line just like I did. So for x is greater than 2, we're going to do something a little bit different. X equals 2 is this line, right? Every point on this line is where x equals 2. Well, x being greater than 2 isn't going to be any of those points because all those points are where x is 2. So I want all the points that are greater than 2. So I need to draw this line anyway, but it's going to act as a barrier. It's going to divide up our coordinate plane into 2 spots. So here's what I mean by that. X equals 2 is what we're going to read here. We're going to think of it just like as x equals 2. And we're going to find where x is 2. Well, here's x, here's y. X is 2 is right here, just like it was before. And then we're going to draw a line, a dashed line, up and down through that point to show all possible values where x is 2. And we do it dashed because it's not including this line. Because we don't want to know where x is 2. We want to know where it's greater than 2. So this is where x is 2. We're not going to count that. But everything that's greater than that line is going to fit for our solution. So numbers like 3 is greater than 2, or 5 is greater than 2, or 6 is greater than 2. And all those numbers are over here, right? 3, 4, 5, all of them are right over here. So anything on this side is going to be a solution. So normally our area of solution is really thin. It's the thickness of a line. We kind of color that line in, right? But here, our solution is not on the line. It's actually everything to the right of that line. So we have to color in all of this area over here. I'm going to do the same thing with this one right here. Let's do y is less than negative 3. So now it's an inequality because it doesn't have an equal sign. And when I go to graph it, I'm going to use a dashed line because, again, it's not interested where y is negative 3. It's interested in y is less than negative 3. So we're going to make a boundary line. Here's x, here's y. And when we go to graph this, we're going to graph it just like y equals negative 3. Here's where y is negative 3 on the y-axis. And we know that this is going to be a horizontal line because x could be anything. All of these points are where y is negative 3. Now, I made a mistake. This line isn't going to be a solid line. It's going to be a dashed or dotted line because it doesn't include all the values on this line. So I'm going to do a little bit of this. This probably annoys a lot of your math teachers. But I do it all the time because I forget to do the right dashing. So doesn't include everything that's on this line. Here, all of those points were solutions. Right here was negative 3, 1 comma negative 3. So that was a possible solution for our equation. 3 comma negative 3, that's also a possible solution. Any of these is where y is negative 3, and that's what we're looking for, right? Where y is negative 3. Here it's where y is less than negative 3, so it's not going to include this line because that's where y is negative 3. So where is it less than negative 3? Well, greater than negative 3 would be this way, right? Because that's negative 2, negative 1, 0, 1, 2, 3, 4, 5. Those are all bigger than negative 3. So if we want less than, we're talking about everything underneath it. And so any point down here will work as a solution. And if you check it, it works. Like this point right here is at positive 2, comma, negative 6. So is this a coordinate where the y value is less than negative 3? Yeah, it's negative 6. It works. Same thing if we go back over here. Any point over here will work. So if I choose this point right here, which appears to be 1, 2, 3, 4, 5, comma 2. Is that a point where the x value is greater than 2? Yes, it is. Any point over here will be where the x value is greater than 2. Notice if we have a point on our line, it'll be where x is 2, and we don't want that. That's why we did a dashed line. Same thing here. The line represents where y is negative 3, and we want something that's less than, which is all the points down here. So those are some simple ones. Hopefully you're not too confused by these anymore and how they look. We just have vertical and horizontal lines coming about from these. We can also get a little more complicated. So for instance, if we had an equation like y equals 2x plus 1. Now we know how to graph that. That's in slope-intercept form. And this is an equation, so all we have to do is draw a line. And so what I do is I plot my y-intercept first, because that's slope-intercept, and our intercept goes first on our y-axis. And then we have 2 for our slope. So we go up 2 over 1, up 2 over 1, and keep doing this and do the reverse if we want. Down 2 over 1, the reverse direction. And we get our line. And this line is going to be a solid line because it's asking where is y 2x plus 1? Well, it's any of these points right here is where y is 2x plus 1. Because no matter what my y value is for one of these coordinates, when I take the x value and plug it in, I get the y value. I times it by 2 and add 1, and I do get y. So all of these are possible solutions to this equation. When I want to talk about an inequality, using the same idea, maybe instead of y equals 2x plus 1, y is greater than 2x plus 1. And I go to graph this. X-axis, y-axis. I do the same thing, except this is going to be a dashed line because it's not asking where y is 2x plus 1. It's asking where y is greater than 2x plus 1. So it's not going to include the line where y is 2x, or 2x plus 1. It's going to include everything above it, everything greater than it. So I'm going to do the same line. 1 is my y-intercept, and then up 2 over 1 is my slope, etc., etc. And then I'm going to draw that line. Remember, I'm going to do a dash this time because I don't want to include this line. This is just a divider line. This line represents all the points where y is 2x plus 1, which is not what I'm interested in. I want to know where y is greater than 2x plus 1. So how do I know where to shade? Well, it gets kind of obvious when you get more used to this stuff. But for now, I think the best way is to just check. So what we're going to do is we're going to pick a point on either side of this line. Now you'll notice that the origin down here at 0, 0 is not on the line. So if we test that point and it plugs into this equation and makes a true statement, we know that the solution is over here with this point. It's one of our solutions. If it is not a true statement when we plug it in, we know it's not part of the solution, so we shade the other side. So I'm going to plug in 0, 0 and test if that's a solution to our inequality. So when I plug it in, I get 0 for y and 0 for x. 0 is greater than 2x plus 1. So I get 2 times 0, which is 0, add 1 is 1. And I ask myself, is 0 greater than 1? And of course it's not. 0 is less than 1. So that's a false statement. And if that's a false statement, then this must not be part of the solution, which means this side must not be part of the solution. So I know that the solutions all lie over here. For instance, if you were to check this point right here, which is negative 3, 2. If you were to check that point in this, so if we were to plug it in here, we've got 2 for y greater than 2 times negative 3 plugged in for x plus 1. We get negative 6 plus 1. And then negative 6 plus 1 is minus 5. And we ask ourselves, is 2 greater than minus 5? And the answer is yes, that is a true statement. So this point is part of the solution. This side is where all the solutions are. Any point on this line would not work. So for instance, if I plugged in this point right here, which is our y-intercept, 0, 1. If I plugged in 1 for y and 0 for x, I would get 1 is greater than 1, which is not a true statement. So the line is not included here. That's why we have to dash it. The last two things I need to show you are what happens if we have a greater than or equal to sign or a less than or equal to sign. It's pretty easy. Nothing crazy. So I'm going to give you the exact same equation. And this time I'm going to use less than or equal to. So y is less than or equal to 2x plus 1. Again, we graph it just like y equals 2x plus 1. Slope and intercept. So intercept is 1, slope is 2. Up 2 over 1, up 2 over 1, up 2 over 1 in reverse. And when I draw this line, it is going to be a solid line because remember, what we're talking about now is where y is less than 2x plus 1 or equal. That's what the bottom line means. So it does include the line because the line is where y is equal to 2x plus 1. Right? Just like it was before. So now it's a solid line. And now we have to choose which side to shade. Now, you might be pretty clever and realize, well, when y was greater than, it was on this side. So when it's less than, it must be this side. And we can check that. Let's check a point on this side. Again, let's check the origin. If you can check the origin, it's always a good point to try. If it was on the line, we couldn't check it, but since it's not, we can. The origin is 0, 0. And if we try it, we get 0 is less than or equal to 2 times 0 plus 1. 2 times 0 is 0, plus 1 is 1. And we get 1 is greater than or equal to 0, or 0 is less than or equal to 1. Is 0 less than or equal to 1? Yes, it's true, which means this is the side where the solution lies. All of these points over here would work in this inequality. None of the points over here would. They'd all break if you tried them, like if we tried this point over here, maybe negative 3, 2. If we plug that in, we get 2 for y, negative 3 for x. Negative 6 plus 1 is negative 5, and we'd say 2 is less than or equal to negative 5, and of course that's not true because 2 is greater than, so that's not part of the solution. Over here is where our solution is, and it includes this line. If I were to check this point right here, like we did in the last example, our y-intercept is 0, 1, I'd get 1 for y and 0 for x, and I'd say 2 times 0 is 0, plus 1 is 1, and I'd get 1 is less than or equal to 1. Now it's not less than 1. 1 is equal to 1. However, so it does include this line. So again, the key here is to know that when we're talking about greater than, we do a dashed line, and when we're talking about less than or equal to, we do a solid line. So that or equal to allows us to make a solid line, just like we used to when we did equalities, because it's equal or equal to. And anything without that line in the bottom is going to be a dashed line. So last thing I need to show you, because for the most part, these seem pretty similar to our equalities, right? You graph the line just like you would for this, and then you decide whether it's dashed or not. In this case, it would be solid. And then you just color, right? You choose a point on either side, and you test it, and then you color the side that works. So the one last thing that you need to watch out for is when we have equations not in slope-intercept form and we want to move stuff around. Whenever you move stuff around with an inequality, you have to be very careful. So for instance, if I have, let's do 2x minus 3y is less than 6. So again, we can treat this just like an equal sign. However, there's one case where we can't. So let me show you what happens. First, we want to get y on its own to get into y equals mx plus b form. So we subtract 2x to both sides. moving that whole term over, and we get negative 3y is greater than the negative 2x I moved, plus the 6 that was already there. And then when I need to get rid of that negative 3 in front of the y, again, I need to divide it because I want to separate them, and I divide by a negative number. Whenever you divide or multiply by a negative number in inequalities, you have to remember to flip the sign. So that sign right now is less than. I have to change it to greater than because I divided by a negative number. So whenever you divide or multiply by a negative number, you have to remember to flip the sign, otherwise your inequality gets goofed. It's a little bit different than an equation, right? There's no way to flip an equation when you divide or multiply by a negative. And when we divide, we get 2 negatives make a positive. 2 divided by 3 is 2/3 x. 6 divided by negative 3 is minus 2. So now we can graph that. Again, it's important to remember to flip that sign when you divide by a negative number or multiply by a negative number. And we did. And I asked first, before I graph inequalities, is it going to be a dashed or a solid line? And the answer is dashed, because it is not greater than or equal to, it's just greater than. So when I go to graph this line, I'll graph it in pink. I am in slope-intercept form, so I go to minus 2 for my intercept. And then I use slope to find my next point, up 2 over 3. 2 points is enough to make a line if you have straight edge, so I'll do that right now. And again, it's dashed, because it's greater than, not greater than or equal to. And then we pick a point to test to see if it works. So I'm going to pick 0, 0, an easy point to test. And when I plug it in, I get 0 is greater than 2/3 times 0 minus 2. Well, 2/3 times 0 is 0. So I ask, is 0 greater than negative 2? And the answer is yes. True. So this is part of the solution. So everything on this side of our dividing line, our boundary line, is a possible solution. If you were to check a point on this side, you would find out it would be a false answer, so it's not a solution. Any point on this side would work. If you tested something on the line, like this point right here, that y-intercept, which is at 0 minus 2, you'd find it didn't work. So it would not work. So negative 2 is greater than 0 minus 2. Negative 2 is greater than negative 2? Nope. Negative 2 is equal to negative 2. But it's not greater than, so it does not include this line. Although this line is the boundary between solutions and non-solutions, so we do need to draw it. That's the importance of that boundary line there. So again, when you're dealing with something like this, to get it in slope-intercept form, you got to move stuff around. Be careful when you divide or multiply by a negative number. You have to remember to flip the inequality. It was less than, now it's greater than. And then you just graph it like we did for the last ones. Treat it like an equality, draw the line, make sure you check to see if it's dashed or not, then pick a point on either side, test it. If it's true, color that side. If it's false, color the other side. For this one, we tested 0, 0. It was true, so we colored in this side to show all of our solutions. So that's your basic intro to linear inequalities with 2 variables. We did, at the beginning, I showed you some basic ones with single variables. These guys right here, you should be able to do those as well, so make sure you're able to draw these type of lines. I know these can get confusing because they're so simplistic, there's so little information there, and there's no slope or intercept. We freak out. But again, ask yourself, where does x equals 2? It equals 2 right there. It doesn't say anything about y, so we go up and down looking for y, because y is the up and down. Y equals negative 3, where's y negative 3? Right here. Does it say anything about x? No, it doesn't. It just says about y. So we go left and right looking for x because that's where x lives, in the left and right direction. Same thing. When we switch these over, it's just those lines. Again, ask yourself whether it's dashed or not. Those both are dashed. And color the sides where the point works. So that's all it is for that. That's your basic intro to linear inequalities in 2 variables.